Hello students, welcome to a class of topology. Today our topic is closure of a set. Okay, let us define what is a closure. Definition: let X2 be a topological space. X2 be a topological space. Okay, A is any subset of X. If you want to define closure, we want a set first of all. So we consider a subset of the topological space X2. Then what is closure? Closure of a set A is, of the set A is again a set. And it is nothing but intersection of some sets. And that sets have the property that which are closed in the topological space and which also contains the set capital A. That means suppose we have a topological space X2 and A is a subset of the space X. Then closure of a set, if you want to find out closure of the set A, we are considering closed sets in capital X which contains A. We are considering closed sets in capital X which contains A. And you take the intersection of such sets, and that will be the smallest set containing that set, correct? Intersection of all closed sets in capital X which can contain the set capital A. Then that intersection is denoted as the closure of the set, and it is a closure is denoted by a closure A bar and defined as a closure equal to, we are considering intersection of some sets, intersection of some C subset of X such that C is closed. First of all, it should be a closed set and C should contains A. A is contained in C. So we are considering closed sets C in the topological space X2 which can also contain the capital A. Then you consider intersection of such sets. That set is called closure of the set, denoted by A bar, which called a closure. Clear? This is the definition of closure of a set in the topological space. Now you can see that what is A closure? A closure is intersection of closed sets, correct, with some property. So we know that in arbitrary intersection of closed set is again closed. In the previous video we have actually proved that theorem, because if you consider a collection of closed sets in a topological space, then that collection has the four properties, and in that property one among that was it should be closed under arbitrary intersection. Okay, we know that arbitrary intersection of closed sets is closed. Closed sets is closed. Therefore, since A closure is intersection of some closed sets, therefore A closure is a closed set. Closure of a set is always a closed set. A closure is always a closed set. Now, what is the next property we can talk about A closure? A closure is a set of all intersection of all closed sets which can contains A, correct? So that A closure is a set which contains A. And the one property, important property of A and its closure is A is always contained in A closure. Every set is contained in its closure because we are considering intersection of closed sets which contains A. Okay, now the closure also contains some more properties, also has some more properties that will be discussed as a theorem. Let X2 be a topological space. Let X2 be a topological space. Okay, and A comma B are subsets of X. Then the theorem says some properties of closure. First one, A closure is the smallest closed set. The smallest closed set containing A. A closure is the smallest closed set containing A. Second property, if C is if phi closure is always equal to phi. And third property, if A is contained in B, then A closure is contained in B closure. Okay. And fourth property says if A is closed, A is a closed set. If A is closed in X, if and only if A equal to A closure. When a set is closed, its closure is itself. When A equal to its closure, then the set is closed. Okay. And fifth property, A closure, the whole closure is A closure. And the last property, A union B whole closure is equal to A closure union B closure. So these are the some properties of closure of a set. Okay, see the proof. First property says A closure is the smallest closed set containing A. By the definition, A closure equal to intersection of all C subset of X such that C is a closed set and A contained in C. This was the definition of closure. By the definition itself, it is intersection of closed sets. Correct? So that A closure is closed. Clearly, A closure is closed. And can you see that it is the smallest one? A closure is the smallest closed set? Yes. Because since A closure is the arbitrary intersection of sets in this collection, A closure will be contained in every set in this collection. And A closure will be contained in C for every C closed in X such that A contained in C. Correct? Because it is the arbitrary intersection. Intersection is the smallest set contained in every subset in that collection. Correct? So A closure will be contained in for every C in this collection. So that A closure will be the smallest one, which implies A closure is the smallest closed set. It is very easy. Smallest closed set containing A. Now the second property was phi closure is equal to phi. We know that every set is contained in its closure. So for empty set will be contained in its closure is true. Now to prove the reverse implication, you consider phi closure. What is phi closure? Phi closure by definition intersection of all set of all C subset of X such that C is closed and C should contain the set A. Here A is empty set, therefore phi will be contained in C. Now let C equal to empty. I take C as empty. Then is it a closed set? Yes. Empty set is closed in every topological space. Therefore C is a closed set in X. If we choose C equal to empty, then C is a closed set in X. And empty set is contained in C is true because every set is contained in itself. What is C? C equal to empty. Therefore empty contained in empty is a true statement. Therefore empty contained in C is true. So that if you take C as an empty set, then C satisfies the collection's property, this collection property. Therefore C is an element in this collection, which implies empty set, that is the C, is an element in the collection of all C contained in X such that C is closed and empty set is contained in C. Okay, when a set belongs to this collection, then if you take the arbitrary intersection of this collection, that will be contained in this set, correct? Because phi closure is a set, smallest set containing phi. Here phi is an arbitrary set in this collection. Therefore phi closure should be contained in phi. What is a phi closure? Smallest set containing A, containing phi. And what is phi here? Phi also satisfies the property of this collection. So therefore phi is a one among them. Therefore phi closure will be contained in each set in this collection. Therefore phi closure will be contained in phi. This is the second assumption. So second implication. Therefore phi closure will be equal to phi is a true statement. Now the third statement says that A contained in B implies A closure contained in B closure. So assume A is a subset contained in B. A and B are subsets of X. Okay. A is contained in B. We have to prove that A closure is also contained in B closure. Now, let I consider or I define two collections, script A and script B. script A is set of all C subset of X such that C is closed and A is contained in C. You are considering collection of all closed sets in our topological space such that which contains A. This is our topological space X and A is a subset of X. Okay, we are considering all closed sets containing A. This is our collection. And script B is collection of all D subset of X such that D is closed and B is contained in D. What is this collection? This collection consists of closed sets in capital X such that which contains B. Okay. Then we know that the definition of A closure and B closure. We have A closure is equal to intersection of all C subset of X such that C is closed and A contained in C. And this was I denoted as script A. So what is A closure? A closure can be written intersection of script A. Then what is B closure? B closure can be written as intersection of script B. This is the definition of collection in the B closure. Okay. Now, in order to prove A closure is contained in B closure, we are taking some element in this collection and it belongs to this collection. That's we want to prove. Okay, let's see. Let D be a closed set in capital X such that B is contained in D. I take a closed set in collection X such that B is contained in D. What is the meaning of this? Which implies D is an element in script B. Correct? Script B consists of such elements. Okay. Then we have A is an set contained in B. This was our assumption to prove the statement. Okay. When A is contained in B and B is also contained in D implies A will be contained in D. Because A is contained in B and B is contained in D. Then what you get? Which implies D is a closed set in capital X which contains A. D is a closed set in X such that A contained in D. When you have a closed set which contains capital A, then that set will be belongs to our collection script A. Closed set containing A. That's therefore D is an element in script A. Correct? So which implies D is an element in script A. So when you take an element in script B, then that element belongs to script A, which implies the collection script B will be contained in the collection script A. Then what will be their arbitrary intersection? Arbitrary intersection of script B will be contained in arbitrary intersection of script A, and this was B closure. Arbitrary intersection of script B is actually contains, not contained in, contains. So this is the bigger collection, this is the smaller collection, and intersection is increases with the decreasing the collection. So intersection of script B will be contains intersection script A. So this is our B closure. B closure contains A closure, that is A closure is contained in B closure is a proof, which completes the proof. Okay. Now the next property. The property says that when A is closed in X, if and only if A equal to A closure. Okay. Let us try to prove it. So assume that A is a closed set. Assume A is a closed set in X. Okay. And we have every set is contained in itself. Correct? A is contained in A is true for every set. And what is A? Here A is a closed set in X. Okay. We know that but A closure is the smallest closed set. Is the smallest closed set containing A. Here capital A is a set which is closed and which also contains A, but A closure is the smallest one with this property. Therefore, A closure should be contained in A. Correct? But we already have every set is contained in its closure. This is a true statement for every subset. So by 1 and 2, A will be equal to A closure. Okay. Now conversely assume A is equivalent to A closure. We have to prove that A is a closed set. When A equal to A closure, what is A closure? We have A closure is always a closed set. A closure is always a closed set because it is being a intersection of closed sets. Always a closed set. When A closure is a closed set and it is equivalent to A implies A is closed. A is a closed set. Okay. Now the fifth property. A closure, the whole closure equal to A closure. This is what we want to prove. Okay. Ready. Take A closure equal to B. To avoid confusion, I rewrite A closure as B. Then we are looking for B closure equal to B. This is our claim. B closure is equal to B. Okay. How will you say that a closure of a set is equivalent to itself? Only when the set is closed. That was the fourth statement. When a set is closed, that set and its closures are same. Here we want to prove B closure is equal to B. That is, B is a closed set. That is, we need only prove. We already have closure of a set is always closed. Correct? We have closure of a set is always closed. A closure is always closed. What is A closure? B, which implies B closure is closed. When B, not B closure, A closure is denoted as B. So just B is closed. A closure is closed implies B is closed. B is closed. When B is closed by the previous property, B closure will be equal to B. What is B closure? B closure is A closure, the whole closure is equal to A closure. Okay. Then the last property, A union B whole closure is equal to A closure union B closure. Okay. Let us prove contains and contained implications. We have every set is contained in its closure. So A is always contained in A closure and B is always contained in B closure. So which implies A union B will be contained in A closure union B closure. Okay. And also we know that closure of a set is always closed. Therefore A closure is a closed set and B closure is a closed set. And we have finite union of closed set is closed. Since finite union of closed set is closed. If you take finite union of closed sets, that is again closed. Therefore, A closure union B closure is closed. And what is A closure union B closure? A closure union B closure is a closed set which contains the set A union B, which implies A closure union B closure is a closed set. It is a closed set containing a set containing A union B. Okay. Now by the definition, what is A union B whole closure? A union B, but A union B whole closure is the smallest closed set containing A union B. A closure is the smallest closed set containing A. Therefore, A union B is considered as a single set. So, A union B whole closure is the smallest closed set containing A union B. But we already have another closed set, A closure union B closure. This is another closed set which also contains the set A union B. So, which can be true, which implies A union B whole closure. This is the smallest one, which will be contained in another closed set which contains A union B. What is that another closed set? A closure union B closure. So this is some number 1. Now for the reverse simplification, consider we have every A set A is contained in A union B is trivially true, and B is contained in A union B is true. Correct? So by previous property, when two sets A and B says that A contained in B, then its closure also satisfies the same implication. So A contained in B, A union B implies A closure contained in A union B closure is true. Similarly, B contained in A union B implies B closure is contained in A union B whole closure is true. Okay, so which implies A closure union B closure will be contained in A union B whole closure. A closure contained in this set, B closure contained in this set, therefore their union will be contained in this union is the same. So this is the second implication. So from 1 and 2, what you get? A union B whole closure is equal to A closure union B closure. Now, the closure of a set also can be considered as a function. So for that, let X2 be a topological space. I am going to define what is a closure operator. Closure operator. Okay. Consider a topological space X2. Topological space X2. Okay. Then for every A subset of X, we can find out A closure. Correct? Then for every A subset of X, A closure is again a subset of X. Okay. When A closure is A is a subset of X, A closure also belongs to also a subset of X. Therefore, A and A closure are belongs to the power set of X for every A subset. For every A subset of X. Okay. Now I am going to define a function from the power set of X into power set of X. Define a function C from P of X to P of X. Actually, what is P of X? P of X is a topology of a discrete topology of capital X. So the closure operator is actually based on the discrete topology to discrete topology. We can consider like that. C from P of X to P of X. Okay. And it is defined as C of P of X contains subset of X, correct? C of A, where A is a subset of X. C of A is defined as A closure. When A is a subset of X, A closure is also a subset of X. So, A belongs to P of X implies A closure also belongs to P of X. So, clearly C is a function from X to X, well-defined function. And since it is a function from P of X to itself, it is called an operator. Okay. Then what are the properties this operator have? All the properties of the above theorem. What was the properties? C of empty. What is C of empty? That is empty closure. What was empty closure? Empty closure is empty. C of empty equal to empty satisfies. And what is C of X? C of X will be X closure. X closure is defined as X. And third property, if A is contained in B, then closure, A closure contained in B closure. That is C of A contained in C of B. Correct? If A is closed in X, A is closed subset in X, because there is a topology, correct? Therefore, we can talk about the closedness of the set. A is closed in X if and only if A equal to C of A. And A closure, the whole closure was A closure. So, C of A will be C of A. And I can say that countable union, but A union B, closure of A union B equal to A closure union B closure. Here I can say C of A union B will be equal to C of A union C of B. Actually, this union can be extended to a finite union. Okay. So, C is a function, or C is an operator which satisfies all of these properties. This operator is called a closure operator, which is defined on P of X, where X2 is a topological space. Okay. So when you have a topological space, then we can define a closure operator using that topological idea. Exactly the closedness of the set. Now the reverse or the converse part of the statement. Suppose we have a set x and there is some function theta or some c from p of x to p of x with some properties, then is there exist a topology? Yes. By using some properties of this closure operator, we can define a topology. Some sets of capital X with some properties, that four properties as empties, that collection should belong theorem says that let X be a non-empty set, okay. Then you consider P of X and let theta is a mapping from P of X to P of X with the properties. So we are just considering a set together with a function from its power set to power set with some properties. The first property is for every A belongs to P of X. A will be contained in theta of A. Okay. And the second property is theta of phi is contained in, that is phi. That means phi is a fixed point of theta. The empty set phi is a fixed point of theta. And third property, theta is idempotent. And the fourth one is theta commutes with a finite union. So when you have a collection, when you have a non-empty set and a function with these properties, then we can develop a topology on X. Then theorem says that there exists a unique topology, denote to on X, such that it has some property such that theta, this function theta, which is nothing but same as the closure operator corresponding to the topology. Theta coincides with the closure operator. When you have a topology on a set X, we can define a closure operator, and closure operator satisfies all of the four properties also. Closure operator C associated with the closure operator C associated with the topology too. Okay, we will prove it. So to prove this theorem, we have to remember a theorem which was discussed in the section of closed sets in the topological space. The theorem says that when you have a non-empty set and a collection of subsets of X, and that collection if that collection satisfies four properties, there will exist a unique topology based on that collection, and that four properties are that empty set and full set belongs to that collection, and that collection is closed under finite union, and the collection is closed under arbitrary intersection. Okay, so then using that collection we can develop a unique topology, and the closed sets with respect to the topology will coincide with that collection. That was our theorem. So now we are going to use that theorem. So for using that theorem, we want a collection of sets with some properties. So I am going to define a collection. Let collection C equal to collection of all A subset of X such that we are considering using all the properties of theta, we are developing a collection C. The collection C consists of subsets of capital X such that when theta of A equal to A itself, you are considering theta is a function from P of X to P of X. So theta maps every subset of capital X into another subset of capital X. When theta maps some subset of X into itself, that kinds of sets belongs to this collection. Okay. Now I am going to prove this collection C have the required properties of the theorem related to closed sets. Okay. So let's see. What about empty set? We have given that theta satisfies all these four properties. We can use all these four properties of theta. By property 3, we have given that theta is an idempotent element. and by property 2 given that empty set phi is a fixed point of theta. We are going to use the second property. By second property of theorem, what you have, empty set is a fixed point of the function theta. Fixed point of the function theta. What do you mean by a fixed point? What is a fixed point of a function? A point is said to be a fixed point of a function f, then f of x is equal to x. When phi is a fixed point of the function theta, implies theta will be fix the point phi. Theta is the function which fix the point phi. So theta of phi will be equal to phi. When theta of phi will be equal to phi, theta of a equal to a, then a will be belongs to this collection. So theta of phi equal to phi implies phi empty set belongs to our collection C. Now, we know that x is a subset of C. Correct? X is a subset of capital X. And what will be theta of x? We have given the first property of theta says that for every a belongs to P of x, for every subset of x, a will be contained in theta of a. So we can write, since x is a subset of x will be contained in theta of x. Correct? X will be contained in theta of x. This is by property 1. Now, what is theta of x? Theta of x is an element in P of x. When it is an element in P of x, theta of x is again a subset of x. Theta of x is an element in P of x, therefore theta of x is a subset of x. So x is a subset of theta of x and theta of x is a subset of x implies x will be equal to theta of x. When it satisfies this condition, x is an element in collection C. Now we are going to prove the third property of that collection, that is the collection C is, we are looking for collection C is closed under arbitrary intersection. Okay, for that we are considering some elements from the collection C. Let collection A alphas are members in C, some arbitrary collection. So we have to prove that intersection alpha A alpha is also belongs to C. Correct? So when you say that intersection alpha A alpha is a member in C, it belongs to C only when theta of intersection alpha A alpha is equal to intersection alpha A alpha. Theta of A equal to A, then only A will be belongs to collection C. So if you want to prove intersection alpha A alpha belongs to C, we have to verify that theta of intersection alpha A alpha is equivalent to intersection alpha A alpha. So to prove intersection alpha A alpha belongs to C, we want theta of intersection alpha A alpha equal to intersection alpha A alpha. Okay, by property 1 we have A will be contained in theta of A for every A subset of x, or every A belongs to P of x. Here all A alphas are members in C. Members in C means they are all subset of capital X, so that their intersection is also a subset of x. Since for every alpha, A alpha is a subset of x, implies intersection alpha A alpha is again a subset of x. So it is also an element in P of x. Therefore, this property will be satisfied for this set. So which implies intersection alpha A alpha will be contained in theta of intersection alpha A alpha. So this is one implication. Now to prove the reverse. Now for the reverse one, we have, what is intersection alpha A alpha? Intersection A alpha is the smallest set contained in all A alphas. So which will be clearly contained in A alpha for every alpha, because this intersection is the smallest one. Therefore it should be belongs to all these sets belongs to this intersection, considering for this intersection. So intersection alpha A alpha will be contained in A alpha for every alpha. Then you apply theta as a function theta in intersection alpha A alpha will be contained in theta of A alpha. Correct. Now, what are A alpha? A alphas are came from elements in C. Since A alpha is an element in C for every alpha, implies theta of A alpha will be equal to A alpha itself. Therefore, theta of intersection alpha A alpha, which will be contained in theta of A alpha, that is equal to A alpha. So, theta of intersection alpha A alpha will be contained in A alpha for every alpha. So, which implies theta of, this is theta, intersection alpha A alpha will be contained, since it is belongs to A alpha for every alpha, it is also belongs to intersection alpha every A alpha. So, suppose this is equation number 2, then by 1 and 2 we can say that theta of intersection alpha A alpha will be equal to intersection alpha A alpha. Intersection alpha A alpha will be equal to intersection alpha A alpha. When intersection alpha A alpha satisfies this condition, this set belongs to our collection. So, C is closed under arbitrary intersection is true. Now, to verify, C is closed under finite union. Okay. Now, before proving the fourth condition, actually here we used one relation. Intersection alpha A alpha contained in A alpha implies theta of this set is contained in theta of this. Okay. And which was actually used by theta commutes with the finite union. No. When A contained in B, theta of A will be contained in theta of B. That is actually we want to prove that statement. Then only we can write it, right? Okay, I will do it as a result here. If A is contained in B, then theta of A will be contained in theta of B. Okay. Suppose A is contained in B, then A can be or B can be written as A union B minus A. A union B minus A will be equal to B itself. Then by the property of 4, theta commutes with the finite union. So, we can apply theta here. Theta of B will be equal to theta of A union theta of B minus A. Correct? So, theta of B will be equal to union of two sets. So, when union of two sets together form theta of B. So, which implies theta of A is a component of theta of B. So, theta of A will be contained in theta of B is true. So, using this idea, I written intersection alpha A alpha will be contained in A alpha implies theta of A is contained in this. Okay, please remember it. Please note this with the proof. Now, we will prove the fourth condition of the collection. C is closed under finite union. For that, let A1, A2, etc. A and B some finitely many sets in C. We are going to prove that union. What is our claim? Union I equal to 1 to n AI is also a member in C. This is what we want. For that, we want theta of this set is equal to this set itself. Okay. Now, by the fourth property of the function theta, which is given in the theorem by 4 of given in the given theorem, theta commutes with the finite union. Correct? So, theta of union I equal to 1 to n AI will be equal to union I equal to 1 to n theta of AI. Because theta commutes with the union, which is the meaning of that statement. And what is theta of AI? A1, A2, etc. ANs are members in C. So, which implies theta of AI will be equal to AI for every I equal to 1, 2, 3, etc. n. Because all are elements in C. Elements in C have this property. So, theta of AI is AI itself. So, union I equal to 1 to n AI. So, theta of union equal to union, which implies union I equal to 1 to n AI is also an element in C. Therefore, C has the required properties of a theorem stated in the section of closed sets. Therefore, by that theorem, X has a topology. There exists X has a unique topology tau, which coincides with the property that the closed sets by tau is similar as or equivalently the collection C. Property that not which with the property that the closed sets by tau is equivalent to collection C. So we get a topology now, but we want there is a topology, unique topology tau on X with the coincides with the closure operator coincides with the given function theta. Okay, now we have the closed set collection, closed set C. Okay, when we have this statement, the closed set collection of closed sets with respect to tau will be equivalent to our collection C itself. And what is our collection C? Collection C consists of set of all A subset of X such that theta of A equal to A. That means this collection C is nothing but collection of closed sets in the by the topology tau. That is the meaning now. So this C is equal to collection of closed sets by tau. Correct? So what are the closed sets property? If A is an element in this collection, then A is closed. When A is closed, A will be equal to A closure. When a set is closed, then A will be equal to its closure. Correct? So collection C have the property that theta of A will be equal to A. Here A equal to A closure. What is A closure? A closure can be considered C of A, where C is a closure operator. Where C is the closure operator given by tau. Closure operator given by tau. So already we have, when A is an element in this collection, theta of A will be equal to A. For this A can be written A, but we have A equal to theta of A for every A in C. So which implies this A will be equal to A closure. A closure will be equal to theta of A for every A in C. Then A closure is defined as C of A. C of A will be equal to theta of A for every A in C. So which implies the closure operator and the function theta coincides here. Which implies the closure operator and the given function theta coincides. Okay.